The world's largest source of recycled steel doesn't come from mines. Guess where it comes from? The automotive recycling industry, often called the second life of cars, which supplies the global market with a colossal flow of steel each year. In the United States alone, more than 12 million vehicles are dismantled and recycled annually, transforming car huts into veritable artificial steel mines, among the most efficient ever created by humanity. Every car we thought was reaching the end of its life is actually beginning a new journey. In this video, we'll see how used vehicles are transformed into raw materials, ready to build infrastructure, fuel industry, and even give birth to the next generation of automobiles. You buy a car for $48,000. After 10 years on the road, what value does it retain when it enters the recycling process? Behind this question lies a $60 billion a year industry, where millions of vehicles are dismantled, crushed, and reborn as new raw materials. This cycle provides hundreds of thousands of jobs, significantly reduces the costs associated with metal smelting, and significantly reduces the environmental burden. And if iron ore represents a natural mine, then end-of-life cars are a limitless artificial mine. Each recycling cycle saves up to 74% energy compared to extracting new ores. On average, 75% of a vehicle's weight can be recovered, from steel to aluminum, including glass and plastics. As a result, each year, hundreds of millions of tons of materials are reborn and continue their journey in the form of buildings, everyday products, and even new cars. When a car reaches the end of its life, it is taken to the receiving area of a recycling plant. There, technicians record its vehicle identification number, engine number, year of manufacture, general condition, and all associated documents. They photograph it, assign it a tracking code, and integrate all the data into a digital management system. This step not only guarantees full traceability of the process, but also allows for the residual value of each vehicle to be assessed. The inspection focuses on reusable components, such as the engine, gearbox, electronics, and interior parts. These usable items are isolated and feed the multi-billion-dollar used parts market. Vehicles that are too damaged or completely worn out, on the other hand, are sent directly to disassembly for material recovery. Once this step is complete, the vehicles are organized into batches in the yard, lined up, and ready to enter the processing line in a clear and systematic manner. Few people know this, but in the United States, more than 95% of end-of-life vehicles pass through this system, making cars the most recycled consumer product in the world. Thanks to this level of organization, each vehicle maximizes its recoverable value and contributes to the economy. Once the inspection is complete, the vehicle enters the processing area. The first step is to remove the battery, the main electrical hazard still present. In combustion engine cars, the lead-acid battery is removed immediately. This type achieves a recycling rate of over 98%, as the lead, plastic, and even sulfuric acid can be reused to make new batteries. For hybrid and electric vehicles, the much larger lithium-ion battery packs require an even more stringent procedure. They are carefully detached, securely packaged, and shipped to specialized centers. Only after the complete electrical system has been removed can the vehicle be further dismantled. After this step, the car is placed on a platform to extract fluids: gasoline, engine oil, transmission fluid, brake fluid, coolant, and even air conditioning refrigerant. Hydraulic clamps secure the chassis, while a steel probe pierces the tank and sucks out the fluids using a high-pressure water vacuum pump. On average, a decommissioned vehicle still contains several gallons of fuel and fluid, enough to cause fire, explosion, or pollution if not handled properly. Within minutes, everything is drained and directed to underground tanks. A notable feature is that nothing is wasted. After filtration, the majority of the recovered fluids are reused to power the plant's forklifts, generators, and other machinery. The remainder is stored for internal needs, significantly reducing energy costs. Throughout this process, pressure sensors, check valves, and sealing plugs ensure a completely closed system, preventing vapors from escaping and ensuring the safety of the line. Once the fluids have been extracted, disassembly of the main components begins. Wheels are usually removed first because they take up a lot of space and are easy to process. Used tires are among the most difficult waste materials to decompose, requiring decades of disposal in landfills. Instead, most are ground into rubber granules for asphalt pavers or playground equipment, while others are used as alternative fuel in industrial furnaces. Steel or aluminum rims are sent directly to the foundry for recycling. Next come the windshields and windows, cut using specialized tools. These laminated glasses, reinforced with a layer of PVB, prevent shattering. Recycling allows for the recovery of glass, but also PVB, which is reused in soundproofing materials and industrial coatings. Next, the doors are dismantled, a seemingly simple element, but made of multiple materials. The steel or aluminum frames are cut to be remelted, while the electric window motors, locking system, and wiring are separated to extract the copper, plastic, and magnet. The interior follows: seats, dashboard, and carpeting. Everything is carefully disassembled and sorted. The cables are stripped to recover the copper, while the plastic and textiles are shredded and transformed into new materials. Finally, the engine and transmission, the heaviest and most valuable mechanical assemblies, are removed. Some are refurbished for resale, others disassembled to extract aluminum, steel, copper, and even precious metals from the catalytic converters. This methodical sequence maximizes the value of each part and prepares for the next step, crushing the car's body. Before entering the press, the car still retains various non-metallic components that are difficult to process, such as twisted exhausts, large plastic panels, and tangled cables. These residues are removed in a pre-treatment area where immense mechanical arms equipped with hydraulic shears come into action. With forces of several tens of tons, these steel jaws tear off the remaining doors, extract exhausts, or reduce radiators in a few seconds. Plastics, foams, and non-meltable materials are immediately discarded. With this raw power, the chassis is quickly cleaned, much faster than by hand. This step acts as a coarse filter, removing materials that could ignite, contaminate the recycled metal, or damage the press. In just a few minutes, the structure is reduced to a clean steel and aluminum shell, ready for compaction. It is then introduced into a massive hydraulic press. Under a crushing force of 150 to 200 tons, a structure of more than 4 meters is compressed into a compact block. Its volume is reduced to 1/10 of the original. Depending on the technology, this process is carried out using different machines. The baler transforms the chassis into a dense, stackable cube that is easy to store and transport. Modern balers can process 25 to 40 vehicles per hour, making them ideal for large sites. The flatbed compressor is preferred for medium or small vehicles. It flattens vehicles into sheets a few dozen centimeters thick. Faster and less energy intensive, it nevertheless offers a lower density, making subsequent crushing more energy intensive. As for the shear baler, it compresses and cuts the vehicle into sections ready for crushing or even direct casting. Different methods, but the same goal: transforming a bulky carcass into uniform metal, ready for a new life. Once compacted, the dense steel bales are fed into a high-capacity industrial crusher, the true heart of the line. Inside, massive steel shafts with interlocking teeth rotate in opposite directions, tearing the block apart in seconds. The metallic crash amplifies the air, and in an instant, a car occupying an entire space is reduced to homogeneous steel fragments. The pace is dizzying. A modern shredder can process 100 to 150 tons of steel per hour, or several hundred vehicles per day. This efficiency allows the automotive recycling industry to operate on a large scale, transforming mountains of scrap into raw material ready for melting. After shredding, the mixture of metals and non-metals moves along a sorting line, using powerful magnets for steel and eddy currents for aluminum and copper. Plastic, rubber, and textiles are disposed of. Recovered steel is compacted into bales for the foundry, while aluminum and copper are separated for other industries. In less than an hour, an abandoned car yields pure, reusable metals, ready to re-enter the production cycle. What was once just a carcass is now compacted, crushed, sorted, and grouped into standardized bales. The recycling journey thus enters a new phase. These blocks are sent to an electric arc furnace. There, they face infernal heat. Graphite electrodes release currents of tens of thousands of amperes, generating an arc similar to artificial lightning. Within minutes, the temperature climbs to over 1,600 degrees Celsius, transforming the steel into melted steel. Hot and molten, they absorb impurities, forming a layer of slag, while jets of oxygen burn away unwanted elements. Sensors and spectrographic analyses continuously monitor the composition to ensure a perfect alloy. From a chaotic heap of worn parts, now emerges a glowing sea of pure steel, ready to be cast into semi-finished products. The refined liquid steel is immediately conveyed to the continuous casting line. A glowing stream flows into water-cooled molds, solidifying on the surface in seconds, while the core remains liquid. Rollers guide the slabs and billets along the line, where they gradually cool. This creates long square bars for construction or flat plates that will be rolled into sheets or coils. Automated thermal saws cut them into standard segments weighing several tons. Each piece is numbered, scanned, and recorded as a batch. From a stocking to a metal form, S-shaped blocks become standardized, opening a new chapter in the cycle. As they leave the reheating furnace, the glowing billets enter the hot rolling mill. There, huge rollers press, stretch, and bend them into uniform sheets or coiled. With each pass, the metal flattens and elongates, evolving from a rough block into regular sheets. Ultra-fast cameras and laser sensors measure every millisecond, monitoring thickness and straightness to ensure perfect precision. This work is reminiscent of a metal sculpture, both powerful and extremely precise. Rolled steel cannot be shipped immediately. It must be cooled in a controlled manner. High-pressure nozzles cover it with a white mist, rapidly lowering the temperature without cracking. Then, powerful fans ensure gradual cooling that preserves its internal structure. Once at a safe temperature, each coil is inspected. An ultrasonic sensor detects hidden cracks. A high-resolution camera analyzes the surface, and a mechanical test measures strength. Only those that pass muster are marked and stored. From its incandescent glow to its masterful strength, steel is ready to serve hundreds of modern industries. Thus, from a seemingly useless old car, recycling opens up a whole new life. It all begins with careful disassembly, safe emptying, and then crushing under hundreds of tons of pressure, followed by the roar of the crusher. The metals are then precisely sorted before being melted down to become new steel. Rolled, cooled, and inspected, the latter becomes a durable and clean material, ready to support construction, industry, and the manufacture of new automobiles. Every end-of-life vehicle, far from being waste, fuels a multi-billion-dollar industry, reduces energy consumption, and relieves natural resources. Recycling is not only an ecological solution, it's also an invisible pillar of the modern economy. Have you ever considered that the car you drive today could one day become the steel of a building, a bridge, or even another car? Share your thoughts in the comments, but don't leave yet. That's not all. The rest of this video will be just as exciting, so stay tuned until the end. And most importantly, don't forget to like, subscribe, and hit the bell so you don't miss any of our upcoming content. Around 200,000 tons of aluminum are produced every day. The United States alone consumes more than 4.6 billion kilograms per year. To meet this colossal demand, millions of tons must be processed. But how does a reddish rock transform into one of the most precious metals on the planet? In this video, you will discover where aluminum comes from and how it is made. Without it, civilization could not survive. This marvel of engineering is everywhere. Aluminum is an essential element of airplanes, automobiles, and high-voltage cables that carry electricity to our homes. Unlike iron, which oxidizes and deteriorates over time, aluminum forms a layer of aluminum oxide on its surface that protects it from corrosion. It is 3 times lighter than steel. Thanks to its low density and high strength, it became the main material for aeronautical construction. However, it was only in 1807 that British chemist Humphrey Davy first identified a metal in a salt called alum. Its identification was easy, but isolating it proved a major challenge. It took about 20 years for Danish chemist Hans Christian Ørsted to extract the metal. Yet the process was so complex and costly that at the beginning of the 19th century, aluminum was worth more than gold. Napoleon III even used aluminum cutlery for his most important guests, while the others had to settle for gold. Everything changed in 1886 when a discovery made aluminum accessible and affordable. Two scientists working independently, the Frenchman Paul Héroult and the American Charles Martin Hall, developed an electrochemical extraction process still used today. They discovered that by dissolving aluminum oxide in a salt called cryolite and applying electricity, the oxygen atoms separated, leaving metallic aluminum behind. This method made it possible to produce aluminum in bulk at a much lower cost, thus revolutionizing the industry. But where does aluminum come from? It lies just beneath our feet. It attracts miners because it is the most abundant metal in the Earth's crust, making up more than 8% of its composition. However, aluminum does not exist in its pure state in nature. Unlike gold and silver, it does not appear as nuggets or veins. It is found only in deposits of reddish bauxite. The richest deposits are located in Australia, Guinea, Brazil, and Jamaica. The Alcoa mine is located in the heart of the Australian mountains. These mountains are mainly composed of bauxite and form the largest mine of this, or in the world, with about 23 million tons extracted per year. However, most bauxite deposits cannot be exploited without first drilling through an underground rock barrier more than 5 meters deep. This requires explosives powerful enough to demolish a 10-story building. The rock is first drilled, then the explosive, made of ammonium nitrate combined with fuel, is inserted. Each month, they use between 700 and 900 tons of ammonium nitrate. Thousands of tons of ore containing aluminum oxide are blasted every day. Each explosion opens about 2 hectares of land and releases between 50,000 and 100,000 tons of ore. Each ton of ore may contain only a few kilograms of aluminum. A large quantity of bauxite must therefore be processed to produce a single ingot. To obtain 1 ton of aluminum, about 4 tons of bauxite are needed. Extraction requires billions of dollars of investment. Today, the price of aluminum is $2.65 per kilogram, and the mining industry invests in large-scale equipment. This excavator is the largest in the world, costing more than $20 million, making it one of the most expensive. Off-road trucks can transport up to 270 tons of bauxite, and the excavator loads 1 ton in just 3 moves. A truck arrives empty and leaves loaded in only 1 minute. The trucks then unload the ore at the processing plant. To extract aluminum from the ore, a refining process called the Bayer process is used. A conveyor belt deposits the ore into a giant rotating drum where enormous steel balls grind it into a fine powder. The bauxite powder is then mixed with a caustic fluid that separates the aluminum oxide from the rest, producing a concentrated aluminum oxide solution. And then comes the most surprising part. This solution dries and forms sandy crystals called alumina, the substance from which aluminum is made. The next step is to isolate the aluminum from the oxygen. To do this, the alumina is transported to an Alcoa production plant. A loaded ship leaves port every 3 days. The alumina it carries will be transformed by a smelter into 35,000 tons of pure aluminum. Every 3 days, a ship arrives with about 100,000 tons of alumina. Its contents are then completely sucked up by a massive industrial vacuum that extracts about 300 tons per hour, emptying the ship in about 5 hours. The material is then deposited onto conveyor belts and transported to the plant where the alumina is introduced into large electrolytic cells filled with molten cryolite. Cryolite lowers the melting point of alumina from 2050 degrees C to about 950 degrees Celsius. To obtain pure aluminum, it is necessary to separate the oxygen atoms that hold it tightly together. This process requires enormous amounts of electricity. That is why aluminum is called electricity in solid form. Electricity consumption represents about 1/3 of the cost of 1 kilogram of aluminum. The energy used by the plant to power the cells could supply 300,000 households. In total, more than 340 megawatts of electricity are consumed each year to produce aluminum. In the electrolytic cells, a low-voltage, high-intensity electric current is applied through carbon anodes and a cathode, thus triggering electrolysis. Electricity flows through copper rods connected to the cells. The aluminum oxide molecules they contain are composed of 2 aluminum atoms and 3 oxygen atoms. The electric current breaks these bonds, separating the atoms. The oxygen rises to the surface of the container and reacts with the carbon anodes to form carbon dioxide, while the denser aluminum sinks to the bottom. After electrolysis, the molten aluminum at about 950 degrees Celsius is separated from the cryolite by suction pumping. This process takes place in continuous cycles every 36 hours to extract the metal from the cells. Once extracted, the liquid aluminum is transferred into a transport crucible, a thermally insulated container designed to maintain the metal's temperature and prevent premature solidification. In the refining furnaces, the aluminum is reheated to remove the remaining impurities using processes such as filtration, which eliminate unwanted elements like hydrogen and oxides. The pure aluminum is then cast into molds to form ingots, then subjected to controlled cooling to ensure solidification without structural defects. Once ready, the ingots are sent to various industries where they become product for the automotive, aerospace, and construction sectors.